Yeah, thank you for inviting me. So this is joint work in progress with, there's a missing with, Nick Ramsey and Saharon Shelah. I hope there won't be any more typos. Okay, so start with the definition. So T is any complete theory, and you have another language containing the original language of T, and T1 an expansion to that language. Then PC of T1T is the class of models of T, which can be expanded to models of T1. Okay? And PC stands for pseudo-elementary class. Okay. And here's the definition of exact saturation. I gave it a couple of times, maybe. T has exact saturation at kappa if T has a kappa saturated model which is not kappa plus saturated. A PC class will have exact saturation at kappa if there is a kappa saturated model model of T which is not kappa plus saturated. Okay, and then T has PC exact saturation if for every T1 PC of T1T has exact saturation in the sense of close to. Okay? Okay. So what is known? So let's talk about exact saturation first. Remember the first thing without PC? So in joint work with Shelah and Pierre, we proved the following results. So first of all, starting with stable theories. So if T is stable, then for all kappa, T has exact saturation at kappa. Next, if T is not stable, then T has exact saturation in all regular cardinals. So only singular cardinals are interesting for unstable theories. Okay. Next, so now we're looking at a singular cardinal, and we assume the continuum hypothesis around that cardinal. Then for NIP, a theory is distal if and only if it does not have exact saturation. So distality is exactly characterized by not having exact saturation, which is easy to believe if you think about the case of DLO. I have to talk about simple theories. So for simple theories, I need an extra condition, which is called the Jensen's square principle. And so it holds under very weak set theoretic assumptions, like in L. And it's very easy to force. And this is a condition. It says there exists a sequence of unbounded closed subsets with this compatibility conditions. But I won't get into it because we're not going to actually use this definition in this talk. But here's the fact we also proved with Pierre and Shelah that if T is simple and kappa satisfies these assumptions, namely test square and the continuum hypothesis, and the cofinality is bigger than T, then T has exact saturation at kappa. Okay, so this was the known results, and we really don't know what's going on in NTP2, for instance. So is there any non-distal theory without exact saturation? Yeah, I don't know. I think we need more tools on NTP2 to solve this. Okay. So next, what about PC classes? Yeah. So this is work of Malliaris and Shelah. They proved that they proved a lot of results on SOP2, and in particular, they proved that SOP2 is maximal in all sorts of orders, in the Kissler order, and also in what they call what is known as the triangle star order. And the latter implies the following: that if T has SOP2, then it has PC singular compactness, meaning the opposite of exact saturation. There is some T1 of cardinality T, such that whenever M is a model of T and can be expanded to a model of T1, if it's mu saturated, then it's also mu plus saturated for every singular cardinal. Okay? Okay. So this is a bit of like how does it look like? So we have that simple theories are containing entropy 1, entropy 2, and so on. So it would be interesting to understand what does having PC exact saturation mean. And yeah, so maybe show that having SOP2 is exactly the same as having, I should have said not having, yeah, another typo. So, yeah, not having PC exact saturation.
Is T theory T1, is it canonical to some extent, or is it?
No, I mean, there is some T1. There is some T1. So given some T, actually, yeah.
Is it exhibited, or is it just an existence?
Actually, yeah, it is kind of exhibited. Yeah, you have this SOP2, but
It can be set.
yeah, exactly. You can't have lots of set theory. But we'll see some example of how this kind of stuff work. Okay, so the first step in understanding this equivalence is to solve this situation in simple theories, right? So first we note that the previous proof. So remember, for unstable theories, any regular cardinal, you'll have exact saturation. So the same proof will show that you have actually PC exact saturation. So only for simple not stable, the only interesting thing is singular cardinals. Okay, and here's a question that they asked, whether the random graph even have PC exact saturation. Okay, so even this wasn't known until now. Okay, so yeah, I can finally state a theorem. So definition, so kappa of T, I just remind you, is the minimal cardinal kappa such that if P is any type, then it doesn't fork over a set of size less than kappa. Okay? So now let's assume the following. T is a complete simple unstable theory, and T1 any extension of T. And kappa is a singular cardinal with some assumptions. Kappa of T is smaller than mu, which is the cofinality of kappa, and T itself is smaller than kappa, and the continuum hypothesis holds, and square kappa holds. So this, we already had these assumptions. Then you have PC exact saturation, namely there is a model of T1 whose reduct to L is kappa saturated but not kappa plus saturated. Okay? So this is a structural theorem. It says if you're simple and unstable, then you can have models for any extension of the theory. You can have models which are saturated in the reduct, but not saturated, exactly saturated. Okay. So let me maybe say something about the idea of the proof so you can get a feeling of it. Okay. So T is simple, so and unstable, so it has independence property, and this is witnessed by some formula phi of xy. Okay. Now, suppose that remember kappa is singular, so kappa is, we can write it as a sum of lambda I, and lambda I are increasing, continuous, and each one is regular. Then we let A alpha, this sequence, A alpha less than kappa, is an indiscernible sequence in L1, which witnesses IP. Okay? So, namely, for every subset, you can code every subset using phi. Now, let's denote for I less than kappa, we just take II to be the initial segment until lambda I. And also, another thing is that we let A bar alpha be the omega sequence starting from alpha. Okay, so far it was some preparation, and this is the main definition of the proof. We look at the class of sequences, AI, I less than mu. So mu is the cofinality, remember? Such that for all I in mu, either AI is empty or it's an elementary substructure of C1. So C1, from the notation, it's clear that C1 is the master model for T1. Okay. AI is smaller than lambda I, and AI could be either empty, or if it's not empty, then it contains the whole sequence II. Remember, there was this II, the sequence witnessing IP. And another thing is that the whole sequence is increasing continuous. And yeah, for all I, and every finite tuple from AI plus 1, there is a club contained in lambda I plus 1, such that for all alpha in this club, the omega tuple, A alpha, remember that was this one, is L1 indiscernible over C. That's the extra condition, most important condition maybe, on this class. And we have an order relation. The order is just the containment in every element. Okay. So yeah, I hope you remember that, because okay, we'll come back to. I'll come back to this slide. So this is the main lemma. You have some member of this class, so it's an increasing, right, an increasing sequence. And you take A to be the domain, so the union of all the AIs. And C is some subset of size less than kappa. And P is a type in the language L over that set, C.
How many variables?
One. X is one variable.
We know variable.
Yeah. We want to prove saturation, so to prove that something is saturated it's enough to realize every one types. So X is one variable, even though it doesn't matter for the proof. So then there is some B, which is bigger than A, namely it's bigger than A in every coordinate, and B, the union of the BI's realizes P. So the union, in particular, the union of the BI's is a model, but that was already clear from the definition because all the AIs were models. Okay. Okay. So that's the main lemma, and the first step in the proof of this lemma, which I'm not going to prove, is to find some I such that P doesn't fork over AI. So this uses the assumption that kappa of T is less or equal than mu. Okay. So kappa of T, remember, that was the first cardinal. So this means that if you have a type over something of size more than kappa, sorry, you have a type over something, then it doesn't fork over something of size less than mu. So this implies that it doesn't, because mu was regular, this implies that it doesn't fork over some AI. Okay, so. Well, yeah, I meant that's a typo. It's supposed to be AI intersected C. Okay, yeah, yeah, thanks. Okay. Now using this lemma and all the set theoretic assumptions, but the proof of this lemma doesn't use any set theory. It's only model theory. And I mean, the proof of this lemma uses simplicity in a very strong way, namely the independence theorem, and all the properties of forking. And so using this lemma, we can, I said find, but it should be construct a model which is kappa saturated and still has this form, the union of AI for this sequence in this class C. But now let me tell you why M is not, even locally, I'm going to define this later, kappa plus saturated. So let me see. So just look at the local type. I'm connected to all the even ones. I'm not connected to all the odd ones. Okay. So this is a type that we know it's consistent because phi witnesses having the independence property, but this type is not realized because of this condition in the end, that for every finite tuple, C, in particular the finite element that realizes this type, there is some club which such that for all elements in this club, the omega sequence starting from that element is indiscernible over this C. So how could it be indiscernible and saying yes, no, yes, no? Okay. So that's the end of the proof. Yeah, actually, the structure of the proof is very similar to the proofs that we had for without the PC, just a simple case. But the proof of the lemma is completely different than the previous proof. Okay. Okay. So maybe just a word about the stable case, because this is kind of new and not all the details were checked. But I would say it's like 95% true. So yeah. So
5% is false.
what?
So 5% of the proof is false.
Okay, so maybe, yeah, 98%. So so what I said there was a pun in the beginning, but you can ignore it. So the statement for stable theories is that if mu is greater than continuum and t is countable, so even countable is a bit complicated, and stable, then t has PC exact saturation in mu if and only if it has a saturated model of size mu. So, which is, namely this theorem says that in the stable case, having PC exact, you can have PC exact saturation exactly when it's obvious that you can. I mean, if you have a saturated model of size mu, then you can, by resplendency, expand it to a model of T1. So this model will not be mu plus saturated because it has size mu. So this shows that one direction is clear here, but the theorem says that this is the only case. And this is in contrast to the simple case where you always had exact saturation. So it also shows that this hope of this being equivalent to SOP2 is just not true, because you sometimes have a stable theory in which you don't have exact saturation, namely if you're not saturated at that cardinal. Okay. But things become much clearer for local saturation, which I'm going to define now. So local saturation, so M is kappa locally saturated if for every local type, so a local type is just a type in a finite set of formulas. But I have to say here, local type infinitely many variables, as opposed to the usual saturation case where people say one variable. I'm not sure actually these are equivalent or not. So every local type over infinitely many variables over some set is realized. So locally saturated is the same thing as saturated, but with M saturated. Okay. So again, I define what is PC having PC local exact saturation. So we say that T has local exact saturation at kappa if T has a kappa locally saturated model, which is not kappa plus locally saturated. Okay, I just add locally everywhere. So a PC class has local exact saturation at kappa if there is a kappa locally saturated model of T, namely which can extend it to a model of T1, which is not kappa plus locally saturated. And the usual notion for T having PC class, PC local exact saturation, says that for every T1 of cardinality T, this class has local exact saturation. Then, okay, now for stable theory, things become much easier. Namely, if T is stable, then for every cardinal kappa greater or equal than the T, T has PC local exact saturation. Okay, it's not very surprising. Oh, wait. So it's not very surprising because locally, every stable theory is like omega stable. I mean, number of local types is small. So locally it's saturated everywhere, so locally it has exact saturation. So this is what it says, okay? Okay, and now I had a question there which I didn't think about at all. So for instance, we can ask about local exact saturation in the NIP case, not about PC, just about exact saturation, and ask whether it's the same as not being distal. Yeah, I'm not sure. I think probably yes. But okay. So let's define. So remember, there was a definition of kappa of t, which you were maybe familiar with. So kappa log of t is similar, but now we look at local types. So kappa log of t is the smallest cardinal kappa, such that any local type doesn't fork over a set of size less than that. Yeah.
Why don't you just work with countable theory all the time?
Because I want to be more general, right? And so, and okay. So this is kappa log. Now, so working with local things is like working with countable things, in a sense. So in particular, for any complete theory, kappa log can be either Aleph0, Aleph1, or infinity. And in the case it's simple, then it could be either Aleph0 or Aleph1. And if it's infinity, then it's not simple. And also, if t is stable, then it's not hard to see that actually it's Aleph0. Namely, every local type doesn't fork over a finite set. That's
if t is simple, then either Aleph0 or Aleph1, or you say if Aleph0 or Aleph1?
No. The first thing you said. If it is simple, then it could be either Aleph0 or Aleph1. And yeah, okay. If not, it's infinity. So definition, a theory is super short if kappa log is Aleph0, namely every local type doesn't fork over a finite set. And this name, actually I didn't know about this name until 2 days ago. And this class was defined by Wagner and Casanovas in terms of dividing chains. And so it's not exactly the same. They didn't define it the same way, but it's equivalent. And yes, so I'm not the only one who made the following mistake, and that if t is low, namely for each formula phi, there exists some k, such that if phi of xa divides, then it k divides, then it is super short. I mean, there is this inclination to believe this because if it is not super short, it means you have a local type which forks over every finite set. And each time it forks with some formula from that set, but then it k divides for a specific k, and then you can construct a tree property, right? This argument sounds legit, but it's not, because you can have conjunction of formulas, finite conjunctions, and this conjunction you have no bound on it. So actually, Wagner and Casanovas also introduced an example of a simple non-super short theory. So yes, okay. So side remarks. So this class, meaning, okay, what I want to say is this class of super short is not just low, and it's not completely trivial.
It implies low.
It implies low. Yeah, I think so. But okay. Yeah. So now let me state a theorem about PC exact situation in the local case. So it says the following. It's very similar to the previous theorem about simple theories, but every time I replace local. Okay, I think that's all I do. I have a complete simple theory, and T1 some expansion, and kappa a singular cardinal with all the set theoretic assumption. One of them is that the cardinality is greater or equal than the kappa log now. Before it was kappa of t, now it's kappa log of t. Then there is local exact situation at kappa. Namely, there is a model of T1 whose reduct to L is kappa locally saturated, but not kappa plus locally saturated. Okay? So there are some differences. So there are some differences in the statement, namely, what am I going to say here? So yeah, the statement is similar, the proof is similar, and the first step in the proof, the main lemma there, the first step is to show that you don't fork over a small set, and it's more or less the same. But the difference in the theorem is that we don't assume unstable now, because before we had a simple non-stable theory, but now we don't need this assumption because we know that for stable theories you always have PC exact saturation. So in particular, if T is super short, then this theorem says something about cardinals of cofinality Aleph0, right? Because one of the conditions here was mu is greater or equal than this. And if it's super short, then this is Aleph0. Okay. So actually, we have an equivalence. Namely, so suppose T is some theory, and kappa is some singular cardinal of cofinality Aleph0, such that all the set theoretic assumptions hold. Then the following are equivalent: T is super short, and T has PC local exact saturation at kappa. Okay, which means again that for every T1, you have a model of T1 which is kappa saturated, but not kappa plus saturated locally. Okay. So also there is a similar statement can be said about super simple theories, because super simple is the same as kappa of T being Aleph0. Okay. So and the same proof is going to show that if you have an unstable theory, yes. Well, maybe you don't need the instability. Okay. Anyway, then if you have an unstable theory and a singular cardinal kappa of cofinality Aleph0, then the following are equivalent: T is super simple, and T has PC exact saturation at kappa. Okay. So what I thought about doing for the next for the time I have, which is a lot, is to go over the proof of the first theorem, and yeah, so this is going to be fun. It's not a very long proof, so I'll probably finish a little bit before time. So what we want to show again is that T is super short, namely kappa of T is Aleph0, if and only if it has exact saturation. So by previous theorem, we know that 1 implies 2. Namely, if you are super short, then you have PC local exact saturation. So we have some theory which is not super short, and in particular, it's not stable because you remember that stable theories are always super short. And we want to find some T1 such that if M is a model of T1, then, and the restriction to L is kappa saturated, then it is also kappa plus saturated. Okay? Okay, so the first step in the proof is to show that since kappa log of T is bigger than Aleph0, so what does this mean? This means you have a type which forks over every finite set. Okay? A local type, a phi type, or a local type, yes, which forks, you have a local type which forks over every finite set. And from this, you can build a tree, right? I mean, we have a tree that we can build a tree, and but the tree will not.
So how do you know that the local types don't change?
Local types don't change. I don't understand the question. No, wait. Kappa plus saturated in the sense of L. It's not kappa plus saturated in the sense of L1, only in the sense of L. So I don't care about L1. So somehow T1 is there to control the behavior of models of the reducts, but I don't look at local types in L1, sorry, only in L.
K log of T was defined as a supremum of all the.
But for L.
For all local types.
But in L, not in L1.
There is a local type. Just tell me there is a local type.
So wait, right. So maybe I'll tell you this. So if saying that kappa log is bigger than Aleph0 means there is a local type which forks over every finite subset. That's what it means, okay? That's the definition. If you look at the definition, that's what it means. So I take this local type, and I can build a tree out of this forking chain, okay? But, so how does this tree look like? It looks like this. You have formulas psi n less than omega, and a tree sequence, okay, such that each formula psi n is a conjunction of instances of phi. I didn't say there was no phi here. That's another typo. So there should be also there exists some phi and all this.
Are there negations somewhere too?
No, you don't need negations. No, because no. Why would you need negations? I mean,
Phi type involves negation.
yeah, you're right. But you can code every finite set by you can code the negation by like you can add another parameter and say if this equals that, and you take the negation. Okay. But that's actually I'm fine with having negations there. That doesn't bother me. So okay, okay. So every formula psi n has this form, and I don't know why. I don't know why I meant by a eta is a eta tuple. I meant yeah. So actually, it should be that's a typo. This should be L. So Ln, and that should be Ln here. And then for every branch in this tree, is consistent, and for every eta, if you look at the successors of eta, then this is 2 inconsistent. Okay, so it's like the tree property, but with 2. Okay, 2 inconsistency instead of k inconsistency, and you replace the formula psi n are blocks of formulas in phi, of instances of phi. Okay, and the proof. Okay, to prove this, there was an argument in a paper of Artyom and Nick that we used using tree indiscernibles. So we start with the tree that we get from this assumption, and we make it very indiscernible, and then we glue things together until they're 2 inconsistent. Okay. So let's say you believe this. Now, using step 1. Okay, maybe I should draw this. Like you have, so step 1 was like this. You have blocks, and each 2 are 2 inconsistent, and so on. Okay. Okay. Yeah. Okay. So using step 1, we can define an extension of T such that, first of all, it has arithmetics in it.
Expansion.
Yeah, expansion, sorry. But is it really illegal to say extension?
Yeah.
Okay. So, so expansion of T. So first of all, it has a predicate that has arithmetics in it. Okay. Secondly, there is some binary function symbol such that if M is a model of T1, and which is αf1 locally saturated, then then for every function from the natural numbers to M, there is some C which codes that function. Okay. So how do we do that? So we just look at the tree. So imagine the tree was the model, and then C should code the branch. Okay. So the function says, okay, for n equals 1, I choose this block, this guy. For n equals 2, I choose this guy. And so C would just be the guy realizing this branch. You can call this. I mean, I'm not saying it like it is, but this is the idea. Okay. The idea is you can call, since local types are, we assumed some local saturation, then all these branches are consistent. So C will be the guy realizing that branch. And then we just add to the language some functions to help us define this. Okay. Okay, so that's it, okay? That's it for T1. No, sorry, maybe we'll add a little bit more later. But next, so what we want to show, we have a model which is locally kappa saturated. So remember, kappa was this cardinal having all these properties, and we want to realize we have a type over a set of size kappa, and we want to realize it because we want to show that it is kappa plus saturated. That's what we want to show. We have a model which is kappa saturated. We want to show it's kappa plus, and we write the domain of that type A we write it as a union of ANs where each guy here is small. And this is possible because kappa is cardinality Aleph 0, okay? So because we assume saturation, there is some Bn realizing this type, okay? Yeah, so I mean the restriction of this type to An. And now we use the previous step to have a function, to have some C such that f of nc equals bn. So this makes sense, okay? So n is a natural number, but it belongs to the model. We assume that the model contains a copy of arithmetics. Okay. Next, step 4. So for each formula, so we have a formula in P, and this formula came from some an. So we define d phi to be the set of m's for which if k is between m and n, yeah, then phi of kc A holds. Okay? So again, we have some formula. This formula belongs to some an. So d phi is the set of m's for which all the intervals, so draw that as well. So we have phi of xa, and it belongs to an. So we look at, this is the natural numbers, and so d phi is the set of m such that in all this interval, this type C realizes this formula. Okay? So d phi is definitely definable, right? In T1, it's definable. So it's a convex definable set, and it contains all natural numbers, right? Bigger than some number n, because remember that for k bigger than n, which is natural, phi of f of kc A holds because it realizes the whole type. This is the choice of bn's. Okay? So it's a convex set containing an n segment of the natural numbers, so it contains a non-standard natural number. A non-standard number. Shouldn't call it natural. Okay, so it contains a non-standard number, and right, m phi. So we have m phi here. Okay, and this is the natural numbers, and m phi is above them. And what we know about m phi, that everything below here realizes this formula phi. Yeah. So there is yeah. So to conclude, it is enough to find some number n, which is non-standard here, but smaller than all the m phi's, right? Because then, by definition, this number m will be contained in all the d phi's. So, sorry, it will not be contained. It will be contained in the interval defined by the d phi, and so it will realize every formula phi. Okay, that makes sense to you? That's the crucial ingredient. So we want to realize a type. So instead, we realize a cut. Okay, and by realizing that cut, and applying the function to it, the resulting element will realize the type. Okay? Okay, so so the set M phi, so P was a local type over a set A. Sorry. Yes. Wait, what am I saying here? Yeah, that's supposed to be kappa, not mu. So yeah, I think I mixed up kappa and mu at some point. So the set M phi, I mean, how big is the type? We want to realize a type of size kappa. So the number of elements in this set M phi is size kappa, but kappa was singular. So the set of elements M phi, this set, will have cofinality smaller than kappa. Yeah, mu should be kappa, okay, in this slide. Okay, so yeah, okay. So now remember that. Wait, did I? Yeah. So D is a cofinal subset. So D is here. D is contained here, and it's of size less than kappa, and it's cofinal going down toward the natural numbers. So it's enough to find some guy which is smaller than D. Okay. Yeah. So now recall that T is unstable, so it has the order property. Okay. Some formula has the order property, and let's assume for simplicity that the natural numbers witness that. Okay. Namely, for every cut, we can realize the following type: psi of xm for m in that cut, but not psi of xm for m not in the cut. Okay? This is the order property. I mean, we know that T is unstable. So we can realize the following type. So psi of xm for every natural number, sorry, but the negation for every m in D. D was smaller than kappa, and we assume kappa saturation, so we can realize that type by some element D, and then I let m be the first number, which is not connected to D. Then it's easy to see that m minus 1. First of all, m minus 1 is non-standard because m is non-standard because all the standard natural numbers are connected to D. So it has to be non-standard, and it exists because all the elements from big D are not connected to M. So this is non-standard, and it's smaller than everything in D, and we're done. Okay? Any questions? So yeah, so this proof shows that I mean, this is the kind of techniques that we use to show that that a theory doesn't have exact saturation. For example, in the stable case, the idea is to use the same kind of thing, using, I mean, the fact that you can code functions, and show that if T is not stable at kappa, then any indiscernible sequence can be extended to an indiscernible sequence of size kappa plus, which means that the model is saturated. There's a test for saturation for stable theories, and it says that if you have an indiscernible sequence, you can always extend it to be as large as the saturation, and we use this kind of using this kind of function to do it.
Expand by arithmetic.
You expand by arithmetic and even finite set theory, and you use again that it's not super stable, so it has this tree, and yeah, it's a little bit more complicated than this, but okay. So yeah, that's it. Thank you.